You're being pulled down right now by a force that no one really understands. Gravity, this invisible thing that keeps your feet on the ground and the moon spinning around Earth. Seems simple, right? An apple falls from the tree. Planets orbit the sun. But here's what will blow your mind. After hundreds of years studying, scientists still don't know exactly what gravity is. Einstein said it's space curving like a bedsheet. Others say it could be tiny particles traveling faster than light. What if gravity isn't a force pulling you down, but the universe itself pushing you? And the scariest part, there might be gravity coming from dimensions we can't even see. Subscribe to the channel, leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. Why do things always fall to the ground when you drop them? Why do you not float away into the air when you jump? These are simple questions, but the answers are not as simple as they first look. Every day, each time you drop your keys, each time you feel your feet press on the floor, and each time you see the moon in the sky, you are seeing the same thing in action. That thing is called gravity. Gravity is a force that pulls all things towards each other. The force is always there, pulling you down to the ground, holding trees and animals and people where they are, pressing the oceans against the surface of Earth. If you go outside and throw a ball in the air, it will always come back down. If you jump as high as you can, you will not keep rising. Instead, you will come down after a moment in the air. When you drop a spoon, you can be sure it will not float or fly up to the ceiling. It always goes down. The reason for all of this is gravity. Gravity does not only work on small things like toys, balls, and people. It also works on very big things in space. The moon circles around the Earth because gravity between the moon and Earth keeps it moving in its path. The Earth does not fly away into space because the sun's gravity holds it in orbit. The planets, the sun, the moon, and even the stars are all connected by this invisible pull. Gravity is not something you can see with your eyes. You do not see gravity the way you see a tree or a cloud. Instead, you see gravity by watching the way things move. Every time something changes its place, a leaf falling, a person walking, a stone rolling down a hill, gravity is part of the reason. Gravity acts on everything that has mass. Mass is what makes something heavy or light. A large rock has more mass than a small stone. An elephant has more mass than a rabbit. The more mass something has, the stronger its pull of gravity. Let us think about the ground you walk on every day. The Earth is very big and very heavy. Compared to you, a mountain, or even a city, the Earth is huge. Because it has so much mass, the Earth's gravity is very strong. This strength is what keeps everything living and non-living pressed to its surface. It is the reason you do not float away, and neither do the cars, houses, or forests. If you swim in an ocean, gravity is what keeps the water from floating off into space. If you climb a tall building and drop a coin, gravity is what makes the coin fall to the ground every time. Gravity works all the time and everywhere, not just in the places you can see. Even in the far reaches of space where there is no air, gravity still pulls. The planets around the sun move in smooth paths because gravity holds them. If gravity did not exist, planets and stars would drift away and never stay together. Nothing would stay in one place for long, and the universe would look very different. You might wonder why you cannot feel gravity in the same way you feel wind or rain. Gravity does not have a sound or a taste or a smell. You only notice gravity by what it does. When you feel your own weight, that is gravity acting. If you stand on a chair and jump down, you feel a force pulling you back to the floor. You never see gravity itself, but you see and feel its effects all the time. Let us imagine you are standing in your kitchen. You pick up an apple. The apple stays in your hand until you let go. If you open your fingers and let the apple go, it drops straight down to the floor. Sometimes people laugh and say, the apple wants to fall, but the apple does not want anything. Gravity pulls it down. The apple has mass and the earth has mass. Gravity works between both of them. When you let go, the apple moves toward the earth, or more exactly, the earth and the apple move toward each other. But because the earth is so much more massive, you only see the apple move. If you look at the night sky and see the bright spots of light, you are looking at stars and planets far away. They are not floating freely. Each one is pulled by gravity, joined together to form groups called galaxies. The stars inside these galaxies spin and move, all kept in order by gravity. Without gravity, every star would travel off in a straight line, never to meet another. There would be no shapes in the sky, no sun, and no planets for people to live on. Gravity helps explain how things move. If you jump, you go up for a moment, then come down. The higher you jump, the faster you come back toward the ground. If you throw a ball, it goes forward, but gravity pulls it down at the same time, so it follows a curved path to the ground. A waterfall flows toward the ground because gravity pulls the water. A person going down a slide is being pulled the whole time by gravity. From the biggest things in the universe to the smallest, gravity shapes how everything moves. But gravity is not only about movement, it also holds things together. The air you breathe is kept close to the earth by gravity. If gravity did not exist, the air would float off and nobody could breathe. The land and oceans stay where they are because gravity holds them down. Even your body depends on gravity. The blood in your body, the food in your stomach, and the bones in your legs all need gravity to work right. The strength of gravity depends on two things: how much mass something has and how close it is to you. The Earth is very massive and you are standing close to it, so the gravity you feel is strong. The moon is smaller and far away, so you feel much less gravity from the moon. But the moon does have some effect. It is gravity from the moon that pulls the oceans and creates tides. That is why the water rises and falls on the beach every day. The sun is even more massive and farther away. Its gravity pulls on the whole Earth and keeps it moving around the sun, making the seasons and the years. If you could travel to another planet, you would find gravity is different there. Some planets are much larger than Earth and some are smaller. For example, if you stood on a planet that was twice as big as Earth with much more mass, you would feel much heavier. It would be harder to jump and you would land on the ground more quickly. On a tiny planet or a moon, you could jump much higher. Astronauts on the moon feel lighter because the moon's gravity is less than Earth's gravity. Gravity does not only pull people and things, it pulls light too. When light passes close to a heavy object like the sun, gravity can bend the path of the light. This does not mean light falls down, but the way it travels through space is changed. Without gravity, even light would keep moving in a straight line and never curve or wrap around stars. From the time you wake up until you go to bed, you live with gravity. You walk, you run, you throw a ball, you drop your pen, and even when you sleep in your bed, gravity is pressing you down. It is such a normal part of life that most people do not think about it at all. But without gravity, nothing would work the way it does. There would be no oceans, no sky, no you. Sometimes you may see pictures of astronauts floating in space. They look like they are free from gravity, but this is not true. Gravity is always there. In space, astronauts still feel gravity, but they are falling around the Earth in a way that makes them feel weightless. They never escape gravity. It only feels different because of the way they are moving. Some people wonder why gravity only pulls things and never pushes them. There is no force that pushes things away from the Earth. Gravity works the same way everywhere, always pulling things together. It never makes things move apart. This is one of the special things about gravity. Why is gravity so strong on Earth, but so weak if you try to pick up a feather? The answer is mass. The Earth has a lot of mass, so gravity is strong. A feather has little mass, so gravity is not as strong on it. That is why you can pick up small things so easily, but you cannot pick up a car or a huge rock. The gravity holding them down is much stronger. Gravity does not turn off or stop. It does not matter if it is day or night, sunny or raining, summer or winter. Gravity is always there, even under the sea or on top of a mountain. Gravity does not change much. The only things that change gravity are mass and distance. If you dug deep into the Earth, gravity would be a little less, because you would be moving closer to the center. If you climbed very, very high, gravity would also be a little less. But for normal life, the change is so small you do not notice it. Even though people and scientists see the effects of gravity all the time, gravity itself is invisible. You cannot take a picture of gravity. Scientists use numbers and careful measurements to study how gravity works. They can measure how fast an apple falls or how heavy you feel. They use tools to see how the moon and planets move. Over many years, people have learned more about gravity, but it still holds many secrets. If you ask, why does gravity exist? The answer is not simple. You may know how it works. Things with more mass pull more. Gravity keeps things together, and it acts all the time. But nobody fully knows what causes gravity deep down. It is something you live with and trust every day, even if its true nature is still a mystery. As you think about gravity, try to notice it in your life. Pick up a ball and let it go. Watch how a bird flies and then lands. Look at the stars at night and remember that gravity is what keeps them shining in the sky, never flying away. Gravity is the reason your world stays in place. It is the first step to understanding why the world is the way it is. The pull of gravity ties together everything you know, from your own body to the biggest stars in the sky. When people try to understand gravity, they often start by thinking about simple things they see every day. For a long time, people noticed that things always fell down when nothing was holding them. Leaves dropped from trees, rain fell from the sky, stones rolled down hills, and people stayed on the ground. Everyone could see that nothing floated away on its own. Even animals and water stayed attached to the earth. People did not have the words or science to talk about gravity, but they saw how it made life possible. Long ago, people made guesses about why things fall. Some thought that heavy things just wanted to be close to the ground. Others thought the earth had a special quality that made it attract things towards it. There were many ideas, and some sounded strange today, but all of them tried to answer the simple question, why do objects come down instead of up or sideways? In very old times, thinkers in places like ancient Greece spent time watching objects move. They tried to give reasons for what they saw. One famous thinker, Aristotle, lived over 2,000 years ago. He said that heavy objects fall faster than lighter ones. He taught that the earth was the natural resting place for most things, so when something fell, it was simply returning to its natural place. Even though this was not exactly right, it was a start at trying to explain gravity. For hundreds and hundreds of years, most people followed what earlier thinkers said. They watched things fall and trusted their eyes. Sometimes they believed heavier things really did fall faster because they seemed to hit the ground before light things. People did not often do tests to check these ideas. They used what they saw or heard, and this became common knowledge. This way of thinking matched what people saw in daily life. As time passed, people began to ask new questions. They wanted to know more about the sky and how planets and stars move. People noticed that the sun, moon, and stars moved in the sky in regular ways. The moon seemed to travel around the earth. The sun appeared to move across the sky each day and each year. This made people wonder if the same force pulling things to the ground also made the moon circle the earth or the earth move around the sun. About 500 years ago, new tools like telescopes helped people study the sky. These tools made it possible to see planets and moons in more detail. Astronomers, the people who study the stars and planets, looked for patterns in how objects moved. They wrote down the times of each movement and tried to make sense of it all. Bit by bit, they saw that there must be something large and powerful holding the moon, earth, and planets in their paths. They believed this pull was similar to what made apples fall to the ground. One of the most important people to study gravity was Isaac Newton, who lived over 300 years ago. He noticed that the way objects fell on Earth might be the same as the way planets moved in the sky. Newton wondered if the force that pulled an apple toward the ground was the same force that held the moon in its path around Earth. He worked hard on this idea and developed a new way to think about gravity. Newton's big idea was that gravity was a force pulling all things with mass toward each other. This force did not just work on Earth. It acted everywhere between all objects all the time. Newton said that every object with mass pulls on every other object with mass, no matter how far apart they are. The strength of this pull depends on how much mass each object has and how far apart they are. The more mass, the stronger the pull. The farther away objects are, the weaker the pull becomes. Newton wrote about his ideas with math and examples. He showed how the same rules could explain falling apples, people standing on the ground, and the moon moving around the Earth. He showed that the reason the moon does not fly away is because Earth's gravity keeps pulling it inward, while the moon's speed in its path keeps it moving around the Earth. The planets move around the sun for the same reason. Gravity keeps them close, but their motion keeps them from falling in. This new idea changed how people saw the world. Instead of believing that gravity only worked on Earth, Newton's way said gravity worked in every place, between everything, all the time. People could now understand why the planets stayed in their orbits, why the stars moved as they did, and why comets visited the sky. Even objects thrown high or moving fast could be understood using the same rules. Newton's law of gravity was tested many times. People dropped things of different weights and sizes. They found that when there was almost no air to slow things down, all objects fell at the same rate, no matter their weight. If you dropped a heavy rock and a small ball from the same height and there was no air, they would reach the ground together. This was different from what Aristotle said, but experiments showed that Newton's ideas fit better with what really happened. With Newton's laws, people could now predict how things would move. Sailors used these ideas to send ships across the oceans, knowing when the moon would cause tides. Astronomers could predict where planets and stars would appear in the sky at any time. Knowing about gravity made it easier to explore, to build, to travel, and to plan. Still, most people did not have to think about gravity every day. They simply saw it working all around them. If a person built a house, they trusted that the roof would not float away. Builders, farmers, sailors, and children all depended on gravity, even if they never thought about how it worked. It was a normal part of life that people trusted completely. Some thinkers used gravity to answer even bigger questions. They wondered why the oceans stayed in place instead of floating into space. Gravity keeps the water, air, land, and everything else close to the Earth. Gravity also makes Earth almost round because it pulls everything toward the center. Gravity is the reason mountains do not grow forever or valleys do not get too deep. Every object, large or small, is shaped by this pull. Gravity also helps explain what happens far away from Earth. The Sun's gravity keeps the Earth and all other planets moving in their orbits. This is what gives us seasons and years. The same gravity shapes what we see at night. The Moon is kept in its path by gravity, and that gives us tides. Even the changes we see as the Moon grows and shrinks each month are caused by how it moves around the Earth. People started to ask deeper questions about gravity. What is mass? Why does gravity act on all mass? Does gravity ever stop? Is it possible to turn off gravity? These questions led to more tests and more learning. For example, astronauts in space still feel a little gravity from Earth, even when they are very far away. The Sun's gravity is felt even farther, across billions of kilometers. Gravity becomes weaker when you go farther from an object, but it never truly goes away. As more and more things were discovered, people wondered if there were exceptions to Newton's ideas. With new machines and measurements, very small things and very heavy things started to show strange behavior. Scientists saw that the laws Newton wrote were very useful for most things, but not for everything. Sometimes planets moved in tiny, unexpected ways. Light from stars bent in strange ways near the Sun. These odd results made people curious once again. Even so, Newton's ideas about gravity helped people for hundreds of years. Farmers, builders, and teachers could use these ideas even if they did not know all the details. Kids playing ball games, sailors using stars to guide their boats, and even miners digging into the earth all trusted gravity to do its job. Some people made their own small experiments. They dropped stones from towers, trying to see how fast they would hit the ground. They watched water pouring from a jug, noticing how it always went straight down. In some places, people even timed how fast objects fell, learning to count seconds and measure distance. All of these things helped people learn more about gravity and made Newton's rules trusted everywhere. As more time passed, new discoveries came. People learned about electricity, magnetism, and other forces. They started to wonder if all forces were similar or if gravity was special. Some noticed that gravity seemed much weaker than other forces. For example, you cannot lift your house, but you can hold a small magnet and pick up a paperclip, even when gravity is pulling it down. This made people ask why gravity is different and if something more basic keeps it working. At the same time, people worked to measure gravity more exactly. They built special tools called balances and pendulums. These could measure the pull of gravity in different places on Earth. People found that gravity changed a little if you went to the top of mountains or traveled to the equator. They learned that not every part of the Earth is exactly the same, so gravity is a little stronger or weaker depending on where you are. Many of the first ideas about gravity worked because they matched what people saw. They worked even if they did not explain why gravity existed. People did not need to know every detail to use the power of gravity every day. As long as the rules could predict what would happen, people could trust them. Over time, these early ideas about gravity slowly changed how people saw the world and the rest of the universe. People realized that the same things happening on Earth were happening in the sky. The Sun, the Moon, and the stars all moved because of gravity. This was a very big step for science because it showed that the rules of nature were the same everywhere. People started to use gravity in new ways. They built tall buildings, careful not to let them fall over. They made better ships and clocks. They looked for ways to measure time by the movement of the Earth and Moon. Even art and music changed as people drew pictures of the sky or wrote songs about the movement of the stars, all linked to what they knew about gravity. The more people learned about gravity, the more questions they had. If gravity pulls on everything, is there a way to block it? Can gravity be stronger or weaker if you use something special? Is the pull of gravity from each part of the Earth added together, or is there something else happening? At each step, new people added their ideas to what others had discovered. Young students learned the basics in school. Builders and workers used gravity without thinking about it. Scientists and teachers passed on ideas, and each new generation learned more. Gravity was not just a trick of nature, but something bigger. It helped shape mountains, oceans, and weather. It was the reason that water flowed down rivers. Birds, animals, and people learned to live with gravity. It became part of all the laws of science, and without it, nothing would work. This slow building of knowledge showed that the world is full of questions. Each answer brings something new, letting people see the world with fresh eyes. With every discovery, people tried to find better words, better tests, and better ways to understand gravity. Each time a ball dropped, a river flowed, or the planets moved in the sky, gravity was at work. Gravity, simple and familiar, changed from just a daily force to one of the most important secrets of nature, shaping everything people could see and even the things they could not. The universe is full of things moving in many different ways, and gravity is what connects everything together. When you look up at the sky during the day and see the sun, or at night and see the stars, you are seeing the results of gravity working far beyond the Earth. This same force that keeps your feet on the ground also reaches across huge distances and holds together things that are very far apart. Gravity is not just something that works on balls, apples, or rain. It shapes the way everything in the universe is arranged and how it all behaves. Stars, planets, moons, and even clouds of gas and dust are all affected by gravity. A star is formed when a large cloud of dust and gas becomes heavy enough to pull itself together. The gravity in the cloud causes it to shrink smaller and smaller, pulling all the parts in towards the center. As the cloud gets smaller, it gets hotter, and finally it becomes a star that shines. If gravity did not exist, the gas and dust would drift away into empty space, and no stars would be born. Gravity does not let go, even after a star is made. The star's gravity pulls on everything nearby. Sometimes the dust and gas left over after a star is formed start to come together too. Gravity causes some of these parts to join and become planets. Each planet moves around its star, held in its path by gravity. Without gravity, the planets would fly away into empty space, and stars would have no planets moving around them. The Earth moves in a wide path around the Sun. This path is called an orbit, and gravity is the reason the Earth follows this path. The Sun is much bigger and heavier than the Earth. The Sun's gravity pulls on the Earth and makes it follow its orbit year after year. If the Sun were not there, the Earth would not move in a circle. The Earth would simply move in a straight line, away from where the Sun used to be. But gravity always keeps the Earth close, turning around the Sun in the same way over and over. Other planets move around the Sun too. Each one is held in its path by gravity. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune move in their own orbits. Each of these orbits happens because of gravity. The Sun's pull on each planet is strong enough to keep each one from floating away. Some of these planets have moons, and those moons move around their planets because of gravity as well. Gravity also shapes the way moons move around planets. The Earth has one moon, and it moves around Earth in about 29½ days. Gravity keeps the moon from drifting away. The pull of gravity from the Earth is stronger than the pull from other things that are farther away, like the Sun or the other planets. The moon also pulls on the Earth just a little, and that makes the water in the oceans rise and fall. These rises and falls are called tides, and people who live near the ocean see them each day. The tides happen because gravity from the moon and the sun pulls on the Earth and the water on it. Every planet and every star has its own gravity. Big planets like Jupiter and Saturn have much stronger gravity than small planets like Mars or Mercury. When you stand on a planet with a lot of mass, you feel more gravity. If you stood on Jupiter, you would feel much heavier than you do on Earth. People on the moon feel lighter because the moon is small and has less gravity. Stars also move in large groups called galaxies. A galaxy is made of billions of stars, all pulled together by gravity. These stars move around the center of the galaxy like planets around the sun, but on a much larger scale. The sun and all the planets that go around it are part of a galaxy called the Milky Way. The gravity from all the stars and from a huge hidden mass in the middle keeps the galaxy shaped like a flat, spinning disk. If there were no gravity, the stars in a galaxy would wander off into space, and there would be no galaxies at all. Gravity shapes not only galaxies, but even the biggest parts of the universe. Galaxies themselves move toward each other because of gravity. Sometimes, two galaxies get close and join together to make one bigger galaxy. This happens very slowly, over billions of years. But it is gravity that brings them together. Gravity even affects the way stars are born and how they die. When a star runs out of the gas it uses for fuel, gravity causes it to change. Some stars grow very big before they end, and gravity causes their outer layers to blow away. The very center shrinks under the pull of gravity until it forms a very small, very heavy object called a white dwarf, a neutron star, or sometimes a black hole. The strongest gravity in the universe is found in black holes, which can pull in anything that comes too close, including light. Because gravity works over huge distances, it takes time for its effects to travel from one place to another. When something very big changes, like when two stars crash together, this sends waves across space. These waves are called gravitational waves. They travel far and can even reach the Earth, where scientists can measure them with special machines. Without gravity, all of these things would not happen. There would be no stars, and so no light in the night sky. There would be no planets for people to live on. Clouds of gas and dust would not come together to make new stars or planets. There would be no galaxies, and the universe would look empty and strange. Gravity is what makes all the things we see in the sky work in order, and what makes it possible for life to exist at all. You can find signs of gravity shaping the universe everywhere you look. Every sunrise and sunset, every night and day, all happen because the Earth moves in its orbit around the sun, held there by gravity. Seasons change because of this motion, following the same pattern each year. The way the Earth spins and moves in its path has been the same for millions of years because gravity never stops pulling. On the ground, you see rivers and streams flowing toward the sea. Gravity pulls the water down the hills and mountains, and it keeps the lakes and oceans in their places. When it rains, the drops fall from the clouds to the ground. Every pebble, every piece of sand, every mountain and valley is shaped by gravity working slowly over a long time. Animals and plants are affected by gravity too. Trees grow tall and straight because they are pulled down by gravity but use energy to grow upward. People and animals walk, run, and jump, always coming back down because gravity is always there. The way your heart pumps blood and the way you use your muscles depend on gravity pressing down on you. Gravity keeps the air close to the Earth so we can breathe. If gravity stopped, the air would not stay near the ground, and life would be impossible. The same is true for oceans and lakes, which would float off if gravity let them go. Every drop of water, every breath of air, and every living animal or plant relies on gravity to keep the world in order. When scientists think about how the universe works, they always need to include gravity. It is the reason the sun is hot and round, the planets move in smooth paths, and the moon stays nearby. It is why there are galaxies far away, why they can take shapes that last billions of years, and why the night sky is full of shining stars. The story of how stars and planets are born is really the story of how gravity builds the universe step by step. First, gravity brings together simple clouds of dust and gas. Over time, these get bigger and bigger until they become hot and bright stars. Around some stars, gravity gathers bits and pieces into new planets. Moons form from the same building, all drawn in by gravity again and again. Sometimes, gravity makes strange things happen. When two stars move too close, they can join together or even explode. Some stars end their life by making bright bursts of light called supernovas. Gravity cleans up the remains, pulling them into new stars or planets or into black holes. In every step, gravity is the secret force working in the background. Gravity also keeps our own solar system stable. Every planet, from Mercury to Neptune, moves in a path around the Sun. Some, like Jupiter and Saturn, are very large and have many moons. Others, like Earth and Mars, are smaller and have fewer moons. Each planet is pulled not only by the Sun, but also by every other planet and moon. The balance between these gravity pulls keeps the planets from crashing into each other or flying away. When people send rockets into space, they have to think about gravity very carefully. To leave the Earth, a rocket must push hard enough to break free from the pull of gravity. This takes a lot of power. Even in space, rockets and satellites feel gravity from the Earth, the Moon, the Sun, and even from other planets. Space is not empty of gravity, it is full of it. Long ago, people only knew about gravity from watching things fall or seeing how objects stayed on the ground. Now people know that gravity is part of everything in the universe. It is not just an earthly force, but the main rule that shapes the universe on every scale. Even light from distant stars is affected by gravity as it travels to our eyes. When you look far out into space, you see galaxies grouped into even larger clusters called galaxy clusters. Gravity holds together these clusters, keeping hundreds or thousands of galaxies moving together for billions of years. Sometimes, even clusters of galaxies come together to make even larger superclusters. Everywhere, gravity is tying the universe together in a web that shapes everything from the smallest grain of dust to the largest groups of galaxies. Not every effect of gravity is easy to see. Some things in space move so slowly or are so far away that you cannot notice them change in your life. But over many years, the small pull of gravity adds up and shapes everything around us. The mountains wear down. The rivers change their paths, and the continents move a little. All of this is gravity working over long times and wide distances. Gravity also affects time in small ways. Scientists have found that clocks run a little bit faster or slower depending on how strong gravity is. Near a very heavy star, time goes a little bit more slowly than far away from it. This happens everywhere, but on Earth it is almost impossible to feel. The power of gravity is what lets everything in the universe work together. It brings about the birth and death of stars. It shapes planets. It joins together gas, dust, and rocks. It creates beautiful shapes in galaxies that last for a very long time. Without gravity, none of this would be possible. Every new discovery in space shows a place where gravity has been at work. When scientists look at other planets, moons, or stars, they always look for the marks of gravity. They see how things stretch, bend, come together, or move apart because of gravity's pull. Sometimes they see things happening that show how strong or weak gravity can be. Even today, people learn new things about how gravity works on the biggest scales. New telescopes and machines help us see farther away and understand more. Each new picture from space shows how gravity shapes the universe. Each new idea helps people answer old questions and ask new ones. Gravity is everywhere, acting on everything, all the time. It is what keeps your feet on the ground and what makes stars shine. It fills all space, reaches every corner, and never stops working. Each day, each year, each age, gravity helps to build and shape the universe from beginning to end. When scientists study gravity across the universe, they measure and predict how everything moves. For hundreds of years, people used simple rules to describe gravity, and these rules helped with many problems. However, there were still many things that these rules could not explain. Some small differences between what scientists predicted and what they saw showed that there had to be another way to think about gravity that could solve more questions. A new way of looking at gravity changed what people understood about space and time. About 110 years ago, a scientist named Albert Einstein had an idea that was new and very different from older ideas. At that time, everyone believed that gravity was only a force that pulls things together. This force made an apple fall, planets move in their orbits, and the stars stay in their places. But Einstein asked if there could be something more going on, something nobody had seen yet. Einstein believed that space and time are not just empty and quiet. He said that space and time can change and curve. Space and time are what let things have distance and move. They are not just big emptiness. Einstein's idea was that very heavy things like stars and planets do not just sit in space. Instead, heavy things bend space and time around them. Even though we cannot see space curving with our eyes, it happens everywhere there is gravity. With this idea, Einstein explained gravity in a new way. When you stand on Earth, you feel yourself pulled to the ground. In Einstein's view, this pull happens because Earth curves space and time. The ground is not flat in the space and time sense. When you try to move, you follow the bending of space and time caused by Earth's mass. You fall to the ground because you are moving along the curve that Earth makes in space and time. Objects that are lighter or farther away feel less of this curve, but everything is affected, even light. This idea is called the theory of general relativity. It is a new description of gravity that goes beyond the old rules. General relativity explains that whenever something with mass exists, it changes the shape of space and time around it. The bigger the mass, the stronger the bending. The Sun, which is much heavier than the Earth, bends space and time much more than the Earth does. Einstein's theory also showed that objects do not simply move because they are pulled. Instead, they move because they follow the shortest and straightest path possible inside bent space and time. When there is no mass, space and time are flat, and things move in straight lines. When there is a star or a planet, space and time become curved, and things move along the curves. This is why the Earth continues to move around the Sun instead of flying off in a straight direction. One of the surprising things about general relativity is that it can also bend the path of light. Light used to be thought of as something that could not be pulled or pushed because it has no mass. But Einstein's ideas showed that even light follows the bending of space and time. When light passes close to the Sun, it curves a little, and this has been seen by scientists during special events called eclipses. Many tests in the last 100 years have confirmed Einstein's ideas, making general relativity one of the most trusted theories in science. Einstein also explained why time itself does not always move at the same speed everywhere. When gravity is very strong, like near a very heavy planet or a star, time moves a little slower than far away, where gravity is weak. This means that if you have two clocks, one close to the surface of the Earth and another very high up. The clock near the Earth will tick just a bit more slowly. These changes in time are very small for people on Earth, but scientists can measure them with very careful tools. This is also important for satellites and machines in space, which must consider this time bending to send correct information. Einstein's way of describing gravity helped scientists explain many things that older ideas could not. For example, general relativity explains why the planet Mercury moves in a slightly different way around the Sun than other planets do. It explains how black holes form when a lot of mass is squeezed into a very small space, making a place where nothing, not even light, can escape. General relativity also tells how very heavy stars send out waves in space when they move fast or crash together. These waves, called gravitational waves, can now be detected with special machines on Earth. There are many strange and powerful examples of what general relativity can show. In space, where things are very big and very heavy, normal rules do not fit, but Einstein's new rules work very well. For most of daily life on Earth, the difference is too small to notice. But when scientists look at planets, stars, and galaxies, they must use general relativity to get the right answers. One clear example is black holes, which are places in space where gravity is very strong. When a star that is many times heavier than the Sun comes to the end of its life, it can collapse under the pull of its own gravity. The mass is squeezed into a very small space, curving space and time so much that nothing can get out, not even light. Black holes do not let anything escape. The place around a black hole where nothing can leave is called the event horizon. Scientists believe there are many black holes in space, and some are at the center of big galaxies. These black holes pull in stars, gas, and even light, and they show just how strong gravity can become. Einstein's idea of space and time being flexible and able to bend was difficult for many people to accept at first, because nobody could see or touch space and time. But experiments and observations tested these ideas by looking closely at how things really behave. During solar eclipses, when the moon blocks the sun, scientists saw that light from stars behind the sun bent more than expected, just as Einstein predicted. When space probes traveled near big planets, they also showed effects that only general relativity could explain. The bending of space and time is not only something that happens with stars and planets. Even simple machines that we use every day need to think about it. For example, the satellites that help people find locations on Earth use clocks. Because these satellites are high above the Earth, the gravity is weaker, and their clocks move just a little faster than clocks on the ground. If these small changes were ignored, the satellites would stop working correctly. The idea that space and time can bend also helps to explain how the universe is changing. Scientists have learned that galaxies are moving away from each other and that space itself is getting bigger. This means that over many billions of years, the universe has grown from being very small and hot to what it is now. Einstein's idea of flexible space helps explain why the universe is expanding and how it began. All these discoveries changed how scientists thought about gravity, but there are still many things that do not have answers. For example, scientists do not know exactly what causes space and time to bend. They do not know if there is something smaller or deeper inside space and time that makes gravity possible. Some people wonder if gravity comes from things too small to see or from places we cannot reach. Today, scientists use general relativity to study the biggest and most powerful parts of the universe, like galaxies and black holes. They use it to plan new kinds of machines and to make new predictions. Every time scientists look at space and see something surprising, they ask if Einstein's rules can explain it. Almost every time, the rules still work. General relativity is not the final answer, but it is the best tool we have to understand big and heavy things in the universe. General relativity is very hard to show in pictures or drawings. It does not look like anything from everyday life, but its effects are real. The way planets move, the way light travels, and the way time passes all change because of gravity's bending of space and time. Many people have wondered if there is something smaller inside gravity. They want to know if gravity is made of tiny pieces, like how matter is made of atoms. For other forces, such as electricity, there are very small things called particles that carry the force. For gravity, scientists think there might be something called a graviton that carries the force. Nobody has ever seen a graviton. It could be that gravity works differently from all other forces, or it could be that we need better tools to find out. Einstein's ideas also make people wonder about the edge of the universe. If space and time bend, can they ever end? Is there a place where gravity stops? Scientists are still working on these questions. They look for new information in the way galaxies move, the way stars shine, and the waves that pass through space. The study of gravity has changed many times as people have found new answers. Each new idea about gravity solves problems that older ideas could not. Even today, no one knows everything about gravity. Every new experiment could bring new facts that change our understanding. General relativity works best for very large things, such as stars, galaxies, and the universe. But for the smallest things, like atoms and tiny particles, general relativity does not always help. The math stops working and there are no clear answers. Scientists are trying to find a way to put together the idea of curved space and time with what they know about atoms and particles. This search for a deeper understanding has led to new ideas. Some scientists think there could be other ways to explain gravity or places in space that we cannot see. There may be hidden places where gravity is different, or there may be new things to discover that change how we see gravity. The questions remain very big and very important because gravity touches everything and everyone in the universe. Learning about general relativity helps people see that gravity is not just about things falling or planets moving. It is about how space and time work, how they change, and how they make the world and universe possible. Gravity shapes not just where things go, but what everything is, how everything began, and how everything will move into the future. The ideas of Einstein have helped guide scientists for more than 100 years, and they are still helping today. Every person who learns about gravity becomes part of the journey to understand one of nature's most important secrets. As new discoveries are made, our picture of gravity will become clearer and more questions will appear, waiting for someone to answer them. Gravity, revealed by Einstein as the bending of space and time, connects every piece of the universe, shapes the life of stars and planets, and even affects the way people use machines on Earth. The search to fully understand gravity keeps going, as the mystery is deep and touches all parts of the world and sky. Einstein's new way of thinking about gravity opened many doors for science, but it also brought new and puzzling questions. Many people began to wonder if what we see is really everything there is to gravity. Even though the bending of space and time explained many things, there are still mysteries no one can fully answer. Gravity helps shape everything in the universe, but there is so much about it that remains hidden or is uncertain, especially when we look for the cause of gravity itself. People often want to know where gravity truly comes from. They see that gravity works with things of all sizes. It holds small drops of water and also brings galaxies together. We can predict how gravity acts, but knowing the real reason it even exists is not easy. Scientists agree on how gravity behaves, but when they ask exactly what gravity is made of, there is no simple answer. To understand other forces in nature, scientists often look for small pieces called particles. For example, the force called electricity has a particle named the photon, and magnetism also uses the photon. These particles carry the force, and scientists can see the effects of these particles in experiments. With gravity, there is no clear proof of a particle like this. Scientists have given the name graviton to the possible particle that might carry the force of gravity, but no one has ever found a graviton or measured one. Gravitons, if they exist, would be smaller than anything we can see. They would move energy of gravity from one place to another, making the invisible force possible. But gravity is different from other forces in many ways. It is much weaker than the others. For example, a small magnet can pick up a nail, working against the whole gravity pull of the Earth, which shows how little gravity pushes compared to other forces. This difference makes it hard to find if gravity really has a particle at all. When scientists use the math that explains other forces and try to apply it to gravity, the numbers stop working. The answers become strange, or the math gives results that are not possible. This happens mostly when studying things that are very, very small, like atoms and the smaller particles inside them. Gravity works perfectly for large things like planets and stars, but it is not clear how it works for tiny things. No one has found a way to put the rules for tiny things together with the rules for gravity, even after many years of trying. Physicists try new experiments and ideas to learn if gravity is more than a bending of space and time. They look for places where the two main ideas of science, general relativity for big things and quantum mechanics for small things, can work together. This is very hard because the two sets of rules are so different. In quantum mechanics, everything is made of tiny, jumping bits and pieces. In general relativity, space and time bend smoothly and have no smallest step. Scientists want to know if space and time themselves could be made of tiny parts, or if gravity happens in another way. Some experiments try to show if gravity could be blocked or changed. For example, scientists look for things that might be able to stop gravity or places where gravity is weaker than it should be. So far, no one has found anything that stops or blocks gravity. It always works the same, and it never turns off. Another puzzle is that scientists cannot see or touch gravity itself. They only see what gravity does, how things fall, how planets move, or how light bends near a big star. With electricity, you can make a spark or feel a shock. With gravity, there is nothing for your eyes to see or hands to touch. Gravity makes no sound, has no color, and does not have pieces you can hold. It is always hidden, working only by moving things or shaping the world. Sometimes, scientists look for gravity waves. These are tiny changes moving through space, made by massive things like stars colliding. When two black holes crash together, they make waves in gravity. These waves are extremely small when they reach the Earth, but with special tools, scientists can notice them. In the year 2015, scientists measured a gravity wave for the first time. The tiny shaking from two faraway black holes reached huge machines on Earth and was seen as small changes in distance. Gravity waves are proof that gravity is something real that can move and change. Gravity is also important for keeping things together on every scale. It holds the air to the Earth and brings together pieces of dust to make planets. It keeps water in the oceans and gives people, animals, and plants weight. If gravity changed, nothing on Earth would stay the same. The movement of the oceans, air, mountains, and all living things depends on gravity being stable. Scientists keep asking if there is a deeper reason why gravity works. Some wonder if gravity is a side effect of something else in the universe. Could it be caused by hidden things that we cannot see? Is there a kind of building block inside gravity? There are ideas that gravity might be connected to energy in empty space or to sea of tiny particles we cannot detect yet. Another thing that puzzles people is how gravity tells one object about another. When the sun moves, how does its gravity reach Earth so quickly? It was once thought that gravity's pull acts in no time, that as soon as something changes, every part of the universe knows. But Einstein's theory said gravity travels at the speed of light. If the sun was to disappear, it would take about 8 minutes for the Earth to feel the change, because that is how long light and gravity take to cross the space between them. Gravity also seems to always act the same everywhere. The gravity you feel on Earth is a little stronger at sea level than at the top of a mountain, but the change is very small. On the Moon, gravity is weaker because the Moon is lighter. On large planets, gravity is stronger. But all around the universe, gravity works by the same rules. It depends only on mass and distance. When looking for the key to gravity, scientists sometimes study the way very small and light things act. Tiny pieces of matter, like electrons and the particles inside atoms, do not move as expected if you only use gravity. Instead, they follow different rules. None of the experiments with these tiny, lightweight particles have ever found a sign of the graviton or any way to connect gravity to the other forces using the same ideas. Another big question is about the strength of gravity. If gravity is so weak compared to other forces, why is it able to shape the universe? This question leads to many possible answers, but none are proven. Some say gravity might leak into other parts of space we cannot see, or that it is spread out over a bigger space. There are also puzzles about the very beginning of the universe. Gravity, together with space, time, matter, and energy, started with the universe itself. In the very young universe, everything was squeezed close together, and gravity may have worked very differently from today. Scientists try to learn about this by looking at the oldest light from space and searching for marks or patterns left by gravity long ago. These marks are hard to find and to study. Even with all these questions, scientists use gravity every day. They can measure how strong it is, watch how it changes when you walk up a hill, or predict how fast a ball falls to the ground. They use gravity to plan trips to other planets and to watch how stars and galaxies move. Yet, when they try to write down exactly what gravity is, they still do not have the final answer. Every time a person trips, a tree drops an apple, or rain falls, gravity is there, doing what it always does. We experience gravity everywhere, but only see its effects, never gravity itself. The search for what gravity truly is, down to its smallest part or cause, is still open. The answers may come from bigger machines, new tools, or by testing the universe with new experiments. Many scientists now work together to look for the missing part of gravity. They build special detectors, create new kinds of experiments, and use computers to test ideas about how gravity can fit with the other forces. Sometimes the answers do not match the questions, and this shows just how tricky gravity is to understand. Some scientists believe that we may find hidden parts of the world that can explain gravity better. For instance, they look for kinds of particles that might act only through gravity, or for new forms of energy that change how gravity moves and acts. Others suggest that perhaps the space and time we see are parts of something larger and stranger. There are also questions about how gravity acts with time. Einstein's theory shows that gravity can slow down or speed up clocks. People use this when they measure time between satellites and the surface of Earth. The changes are very small but very real, and these changes help scientists test if gravity is working as Einstein described. Even with all these mysteries, gravity is the best tool we have for understanding the movement of the planets, stars, and galaxies. Nobody has found a single thing, not even light, that does not answer to gravity. No matter how far people travel or how many new things are discovered, gravity is always part of the story. Still, the basic mystery remains. What creates gravity? Why does it pull instead of push? Is there a particle called the graviton? Do we need new rules or new ways to see the world? Each time scientists answer one question, more follow. Gravity connects all things, but it also leaves big questions open for new explorers. Gravity's special role is clear in science. It is everywhere and always working, but it does not easily show its hidden side. When other forces are measured, they can be turned off, blocked, or focused. Gravity cannot be shielded or closed off. Its power works through everything, and it touches all matter. This makes gravity both simple to feel and hard to describe. People have been trying for many centuries to find the answer, but gravity keeps secrets well. Each experiment, each observation brings us closer, but the final answer might take many more years. Perhaps new machines or a discovery no one expects will help explain what gravity truly is, what it is made of, and where it begins. Until then, gravity keeps shaping the world, making life possible, and building the universe. Even with all the puzzles left, scientists are inspired to keep asking questions, keep building better tools, and keep searching for the hidden heart of gravity. Every step brings the world closer to the real answer of one of nature's greatest mysteries. Gravity is not the only force in nature. Scientists have discovered other forces that are very important too. Every day, people use things like power from electricity or the attraction from magnets. These things work because of forces that are not gravity. When scientists look at the world, they find there are four main forces. Gravity is only one of them. The other three are called electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces works in its own special way. Gravity is the force that pulls all things with mass towards each other. It works all the time and everywhere, and it cannot be turned off. Electromagnetism is the force that makes electricity and magnets work. It can attract some things and push others away. Electromagnetism also makes light, radio waves, and many more things possible. The strong nuclear force holds together the tiny parts inside the nucleus of an atom. The weak nuclear force is what lets atoms change from one kind to another, which helps make the sun shine. Gravity acts on everything with mass, and so does the strong nuclear force, but the strong force only works at distances so small that you cannot see them. Electromagnetism acts on things with charge, like electrons and protons in atoms. The weak force is also only found inside atoms. Gravity is different because it does not matter if something is big or small, hot or cold, or has a charge or not. Gravity pulls on anything as long as it has mass. Electromagnetism is a force people use every day. When you turn on a light, use a radio, or pick up something with a magnet, electromagnetism is working. Electrons move inside wires to make electricity. When you see colors, light from the sun is reaching your eyes. All of this is part of electromagnetism. This force is much stronger than gravity. In some cases, a tiny magnet can pick up a paperclip, even though gravity from the whole Earth is pulling down on it. This means that, compared to electromagnetism, gravity is very weak. Scientists know that electromagnetism uses particles called photons. Photons are very small pieces of energy that carry the force. When light travels, it moves as photons. When electricity moves inside wires, photons help transfer the force. Scientists can make and measure photons in many ways, and people see their effects all the time. For gravity, scientists think there might be a particle called the graviton, but nobody has found one yet. This is a big difference between gravity and other forces. The strong nuclear force is found in the heart of every atom. It holds protons and neutrons together in the nucleus. Without the strong force, atoms would not exist. The strong force works only over very tiny distances, so people cannot see it in everyday life. Scientists have found the particle that carries the strong force, called the gluon. The strong force is the strongest of the four forces, but it does not reach very far from the nucleus of an atom. The weak nuclear force helps atoms change. It allows some atoms to become different kinds of atoms. This force is also only found inside atoms. It makes the sun shine because it lets atoms inside the sun release energy. The weak force is stronger than gravity but weaker than electromagnetism and the strong force. The particle that carries the weak force is called the W and Z boson. When scientists do experiments, they often see how the four forces act in different ways. Gravity keeps the planets, stars, and galaxies together. Electromagnetism gives us light and electricity. The strong and weak forces make atoms what they are. Each force has special rules and works over its own range of distances. Some, like gravity, can be felt over long distances. Others, like the strong and weak forces, only work over very small spaces. One of the strange things about gravity is its weakness. For example, if you rub your feet on the floor and then touch a metal key, you might feel a small spark. That spark is much stronger than gravity, even though it only moves a little charge. The reason gravity seems so powerful is because the Earth is huge and it does not cancel itself out. Electromagnetism and the other forces can act in both directions, pulling and pushing, so they sometimes cancel each other. But gravity only pulls, so everything with mass adds together to make its effect stronger. Scientists try to understand why gravity is so much weaker than the other forces. If gravity were a little stronger, the universe would be very different. If it were weaker, things like stars and planets might not form at all. This special difference makes scientists ask if there is something extra that changes how gravity acts. To study gravity and other forces, scientists look at both very big things and very small things. When they use the math for electromagnetism, strong and weak forces, the numbers work well and answer many questions. But when they try to use the same math with gravity on small scales, it does not work. The rules that apply to atoms and particles do not fit gravity. This is one reason why gravity is still a mystery. Some scientists think the reason gravity is so weak could be because it spreads out through extra parts of space. Most people can only move in 3 directions: forward and back, left and right, up and down. Time moves forward. Some ideas suggest there may be more directions or more hidden dimensions that people cannot see or feel. Gravity might move into these hidden places, making it feel weaker. These ideas are very hard to test, and no one has found proof for extra dimensions yet. Another difference is that electromagnetism can be blocked or shielded. For example, if you put your hand in front of a flashlight, less light will reach the other side. You can wrap a wire around a magnet and block its pull. But gravity cannot be blocked. Even with all the matter in the Earth, nothing blocks gravity from pulling. This also makes gravity unique among the forces. All the other forces use particles that can be seen in experiments. Electricity uses photons, the strong force uses gluons, and the weak force uses W and Z bosons. Scientists sometimes create these particles using big machines called particle accelerators. These machines take small pieces of matter and smash them together at high speeds. When this happens, the particles that carry forces can be made, measured, and studied. So far, no one has made or measured a graviton in these ways. Scientists still do not know if gravity really has a particle. If there is a graviton, it would be very hard to find because gravity is weak and does not act like the other forces. Some experiments look for very tiny changes in the way gravity acts at small steps or short distances, hoping to find a sign of a graviton or something else that could explain gravity. When people use technology every day, they are using forces other than gravity all the time. Phones work because of electromagnetism. Power plants use electricity from magnets, wires, and moving water. Medicine and industry use particles from the strong and weak nuclear forces. Gravity is always there, but it usually acts with the other forces at the same time. All living things use many forces together. Muscles work because of electricity in the nerves. Plants use light from the sun to make food, and light is part of electromagnetism. Atoms in your body are held together by the strong force. Gravity connects everything but is only one part of a much larger world of forces. The four forces also shape the entire universe. Gravity puts planets and stars together, making them round and holding them in place. Electromagnetism makes light, which lets planets warm up and have days and nights. The strong force makes atoms stable for billions of years. The weak force turns atoms into different forms and makes new energy in stars. Many scientists wonder if there is one basic force that makes all these four forces. They try to find a grand unified theory, or theory of everything, that could explain gravity, electromagnetism, the strong force, and the weak force in the same way. So far, only electromagnetism and the weak force have been joined into one set of rules. Gravity does not fit into these rules yet. This search leads scientists to think hard about what makes gravity special. Is gravity made of something even smaller than particles? Does it come from extra parts of space? Are there hidden kinds of matter or energy that change gravity? Each force is different, and each reveals a piece of how nature works. Gravity affects the biggest things and the smallest things in the universe. It is the only force that always acts at every distance, from galaxies that are billions of light years apart to the atoms in your body. Other forces are stronger, but they do not reach as far as gravity. The strong and weak forces only matter inside atomic nuclei, and they fade away outside. Electromagnetism acts on charges but does not change things as far away as gravity does. There are also questions about dark matter and dark energy. These are things that scientists think might exist because of the way galaxies move and how the universe is growing. Dark matter is something that does not give off light or other signals we can see, but its gravity changes how stars move inside galaxies. Dark energy is something that seems to make the universe grow faster and faster. Scientists do not know what dark matter or dark energy really are, but their effects on gravity are very important. Sometimes scientists study very small scales, smashing particles into each other at very high speeds. When they look at the results, they see signs of all the other forces, but have never found a sign of gravity working this way. Only when things are very heavy or very large does gravity become easy to see, such as in stars, black holes, or whole galaxies. Each new experiment brings more knowledge, but also new questions. Why can gravity not be put together with the other forces in one theory? Why is it so weak compared to the others? Why does it only pull and never push? Is there a missing piece, like a new kind of particle or an extra piece of space that can make all the numbers add up? People use what they know about the four forces to build new things, make energy, and help others. As the world changes and new tools are invented, the understanding of forces will grow. Gravity remains both simple and mysterious, acting along with the other forces but showing differences that continue to puzzle scientists. No matter how much is discovered, gravity always stands alone in some ways. It cannot be blocked, turned off, or replaced. It connects all mass, moves across any distance, and shapes the largest and smallest objects. Yet it is always different from the other forces. This is why gravity still holds some of the biggest mysteries left in science. Scientists continue to learn more about gravity by comparing it to what they know about electricity, light, and atomic forces. They look for new patterns, try to find connections, and search for new particles. Each answer opens more questions, just as every discovery about atoms and light helped people learn more about the world. As science grows, the hunt for the truth about gravity and its unique place among the four forces continues. Each experiment and discovery adds another step. Each new idea helps move closer to understanding why gravity is both everywhere and unique. Gravity's mystery, its power, and its differences help remind everyone that there is much more to learn, and that the world is full of surprises that begin with simple questions about how everything stays together. Scientists continue to look for better explanations for gravity and the other forces. Gravity stands out because it behaves differently and does not fit with the single set of rules that explain the small world of atoms. As people try to bring gravity and other forces together, many new ideas have appeared. Some of these ideas are unusual, but they could help explain things that are still hard to understand about gravity. One new idea is that there are parts of space that people cannot see or enter. These hidden parts are called extra dimensions. In daily life, people know about 3 ways to move: forward and backward, side to side, and up and down. Time gives a 4th way, which is moving from the past through now into the future. Scientists wonder if there could be even more directions that are hidden or too small to notice. If these extra dimensions exist, they might change how gravity works and why gravity is so much weaker than the other forces. A group of scientists made a theory called string theory. In string theory, the basic building blocks of everything are not small points, but tiny, vibrating lines called strings. These strings are so small that nobody can see them with present-day tools. In string theory, sometimes space can have as many as 10 or 11 directions. Most of these are rolled up so tight that people cannot see or move in them. This idea could mean that gravity spreads into these extra directions, which would make it seem weaker to people who can only notice movement in 3 directions. String theory tries to combine gravity with other forces in one explanation. It uses math to join gravity, electromagnetism, the strong force, and the weak force. The strings can make the particles that carry each force. For gravity, the string would show up as a graviton if it is real. This might also help explain why gravity has not been found in experiments about tiny particles. If gravitons move into other hidden directions, it makes it hard to detect them. There are other ideas about how gravity could be different from what people now think. Some scientists think there could be hidden shapes or objects inside space itself. These shapes could be very small or very strange, and they might change the power of gravity. Some ideas talk about objects called brains. A brain is a shape that can have more directions than a simple line or surface. Some scientists think that all the things people know, including stars and planets, could be stuck on a brain while gravity spreads out into more places that people cannot see. People have tried to find evidence of extra dimensions by searching for small changes in the way gravity acts at very close distances. Some experiments try to measure gravity between objects only a small distance apart, much smaller than the width of a hair. If gravity changes at a tiny scale, it could mean there are extra dimensions or something else new in space. So far, scientists have not found any clear proof, but they keep making better tools to test their ideas. Another theory is that gravity could come from the way quantum particles act in big groups. This idea comes from the strange rules that control tiny things like electrons and atoms, which act in ways very different from planets and stars. Some scientists wonder if gravity might be the result of how these small things come together and how information is shared among them. These ideas use words like quantum gravity, loop quantum gravity, or emergent gravity. They try to explain how the bending of space and time might come from the actions of tiny particles, instead of just being smooth and unbroken. Some scientists have suggested that gravity could be connected to something called dark matter and dark energy. Dark matter is a name for something scientists cannot see or touch, but that still changes how stars and galaxies move. Dark energy is something that makes the whole universe get bigger, faster and faster. Nobody knows what dark matter and dark energy are, but some new ideas about gravity try to link these mysteries together. If gravity acts differently on very big or very small scales because of dark matter or dark energy, it could explain why the universe grows the way it does. Scientists look at the universe to find clues. They watch how galaxies move and how light bends around stars. Sometimes they see changes that they cannot explain with the rules they have. These mysteries push scientists to think about new possibilities for gravity. For example, scientists have found that the universe is not only getting bigger, but it is growing faster every year. The simple rules of gravity cannot explain this by themselves. Some think that there must be a kind of energy spread through space that pushes everything apart. Others suggest that maybe gravity itself is weaker or stronger over great distances because of hidden things, like extra dimensions or new particles. Another mystery is the way galaxies spin. When scientists look at how fast stars move near the edge of a galaxy, they see that the stars move faster than expected. This should not happen if only the stars and visible gas are giving gravity. Scientists think there must be something more with mass, but that cannot be seen. This is called dark matter. Some ideas say maybe gravity works a little differently on these big scales, or that something about space itself is not as simple as people thought. There are also ideas that gravity might change when two very heavy objects are close together. Some scientists have made rules that let gravity become stronger or weaker under certain conditions. They look for places like black holes or very heavy stars to test these ideas. By studying the way light bends and the way objects move near these places, scientists hope to find proof if gravity changes. To test the new theories, scientists use both experiments and observations. Special machines try to measure gravity at the smallest scales possible. Big telescopes watch the sky to find small changes in how galaxies move or how light bends. Gravity waves, which are gentle ripples made in space when heavy stars or black holes merge, can also give clues about the tiniest details of gravity. When two black holes join, they send waves through space. These waves travel very far, and machines called detectors can feel tiny changes as the waves move through the Earth. By studying these gravity waves, scientists learn if the rules of gravity are the same everywhere and every time. If there is even a small change in the speed, shape, or timing of these waves, it could give evidence for new ideas, like extra dimensions or new particles. The search for the graviton, a possible particle that might carry the force of gravity, continues. Detectors and machines are becoming more sensitive. If a graviton or some new effect from extra dimensions affects experiments, scientists hope to see signs in the data. Some look for missing energy or other hints when tiny particles smash together at very high speeds. One more idea is that the universe itself may have more than one kind of space or energy. Some scientists believe there could be other universes, each with its own kinds of forces and rules. If this is true, what people know about gravity might only be part of a bigger set of possible worlds. These ideas are very new and are not proven, but they help scientists keep asking questions and finding better tests. Some of the new ideas about gravity cannot be checked easily. They use big math problems or need tools that do not exist yet. Sometimes scientists do not agree about which ideas make the most sense. They keep looking for better ways to explain the strange things they see, like dark matter, dark energy, the speed of the universe's growth, and the shape of space on the biggest and smallest scales. Every time scientists see something that does not fit the old rules, they try to think of new explanations. Strange new ideas may sound unusual, but they are an important part of science. Without these new ideas, people would never find answers to the questions gravity keeps hidden. Some scientists look for changes in gravity on Earth too. They use weights, springs, and sensitive balances to see if gravity acts differently at small sizes or in special materials. Others look at how atoms act when they are cold or how small drops of liquid move in space. Each experiment brings more clues to help test old and new ideas. No matter what, gravity keeps acting everywhere. Planets turn around stars, stars move in galaxies, and galaxies join together in groups, all because of gravity. At the same time, people build machines and make pictures of space, hoping to find the smallest hints of what might make gravity work. If scientists can find proof for one of these new ideas, it could change what is known about the world, the way space and time work, the way the universe grows, and the way the smallest and biggest things move could all have new rules. Many people work together across the world, building better machines, sharing experiments, and thinking about better ways to test their ideas. Every new discovery opens more questions about gravity. Some ideas will turn out to be right, and others will be thrown away. All of them help people move closer to the truth about gravity and the universe. Scientists know that answers may not come quickly. Some questions take years, decades, or even longer to solve. Each new idea, test, or discovery adds one more piece to the puzzle. The mystery of gravity pushes scientists to keep looking for new facts and better ideas, and even the wildest theories help shine a light on what is not yet known. Learning about gravity is not just about answering old questions. It is about preparing for the next questions people have not yet thought of. Science grows stronger with every new idea, even those that seem strange at first. Each experiment, each measurement, and each discovery helps people understand their own place in the world and in the universe. As the puzzle of gravity keeps growing, so does the hope that people will one day find answers. Until then, people keep searching, building, and learning, always ready for the next surprise hidden in the way the universe holds itself together. To search for answers about gravity, scientists use many different ways of studying both the world around them and the universe above. They design experiments that make careful measurements of how gravity acts and changes. These experiments take place in places as small as a laboratory and as large as the empty space between stars. Every experiment brings new knowledge and can guide scientists in making better ideas about gravity. One important way to learn about gravity is by looking at how objects fall and move on Earth. Simple experiments drop different masses from the same height to measure how fast they fall. Some scientists use very tall towers to let objects drop for a longer time. Others use vacuum chambers to take away the air, so only gravity is working and not air pushing on the objects. These tests show that gravity pulls on all objects the same way, no matter what they are made of or how heavy they are. In more careful studies, scientists use special machines called balances or pendulums. With a balance, two objects are hung at each end, and the pull of gravity is measured very exactly. By adding small weights or moving the objects farther apart, scientists can see how gravity gets weaker with distance. The math from these experiments matches the rules that Newton described hundreds of years ago and helps confirm what scientists believe. Many times, scientists try to measure gravity in new places. In high mountains or inside deep caves, gravity feels a little different because there is more or less mass beneath you. Some people travel to the North Pole or the equator to see how gravity changes. Careful maps of the Earth's surface include these small changes, and pilots who fly airplanes long distances use information about gravity too. There are also very tiny balances now that can measure changes in gravity so small that they are less than the weight of a single piece of dust. These balances use lasers or sensitive springs and are able to feel the difference when a car drives by or when waves in the ocean move. Some are so exact that they can sense the gravity pull of a person walking in the next room. These small tools help test if gravity changes over very small distances or at very weak levels. Not all experiments happen on Earth. Some scientists use rockets or balloons to bring experiments higher above the ground, to places where gravity is a little weaker. There are even experiments done on the International Space Station, far above the Earth, where astronauts feel almost weightless. On the station, they can see how things move when gravity is almost gone. They throw objects, mix fluids, and grow plants to learn more about what gravity does and how it changes life. Scientists also use earthquakes and the shaking of the ground to study gravity. Very sensitive machines called gravimeters can detect tiny changes in gravity as the Earth moves or as tides shift the oceans. Some gravimeters are placed deep underground where nothing else can move them. Over time, these tools collect information that lets scientists look for patterns and changes all over Earth. When scientists want to study how gravity works with very small things, they use beams of atoms and particles. They let these small things fall or move in ways that let them see if gravity changes at very tiny distances. Some experiments cool atoms until they almost stop moving, then allow them to fall inside a machine and measure their speed and path. Others use lasers to watch how particles act in different places. These careful tests help check if gravity works the same way with tiny things as it does with big things. Looking beyond the Earth, scientists use telescopes to watch the movement of planets, moons, and stars. Every time a planet moves in front of a star or a moon crosses a planet, gravity can be measured in new ways. Images from space telescopes let people see how stars move and bend light, giving new tests of Einstein's theory of general relativity. When starlight passes near a very heavy object, gravity bends the light, an effect called gravitational lensing. This effect can show if the rules of gravity are the same everywhere or if new things are happening in parts of space where people cannot go. One of the most modern ways to study gravity is with gravitational waves. These waves are made when very heavy things like stars or black holes move, crash, or join together. The waves travel through all of space and reach Earth as tiny ripples. To measure them, scientists have made special machines called detectors. These detectors use long tubes with lasers running through them. When a gravitational wave passes by, it changes the length of the tube by a very small amount, less than the width of a single atom. In the year 2015, scientists proved that gravitational waves exist by measuring them for the first time. Since then, many waves have been found, and each one brings new information. By studying these waves, scientists can learn about very heavy stars, black holes, and even how gravity works when things are changing very fast. Gravity waves do not just tell scientists about the objects that made them. They also help check if the rules of gravity are always the same. If a wave is slower, faster, bigger, or smaller than predicted, it can show if gravity acts differently under special conditions or if there might be hidden parts of space or new particles at work. Satellites in space also help measure gravity. Some are made to map the shape of the Earth very exactly. They fly over the oceans, mountains, deserts, and cities, measuring how strong gravity is in each place. These maps are used to track changes in water, like rivers drying up or ice melting at the poles. Some satellites help people find their position on Earth using signals sent from space. These signals need to include small corrections for the way gravity changes time, otherwise they would not be accurate. To look for signs of new kinds of gravity, scientists sometimes send machines far into space. Some spacecraft measure how far they move from the Sun or how fast planets spin. If gravity acts differently far away from Earth, these machines would pick up the change. So far, gravity seems to act by the rules everywhere people can measure, but these experiments keep testing for small differences. Some experiments now look for the graviton, the possible particle that would carry the force of gravity. These experiments use large machines called particle accelerators, where tiny pieces of matter are smashed together at very high speeds. Scientists hope that if gravitons exist, they might show up as missing energy or as a new effect in the way other particles move. So far, no one has found a graviton, but the search continues. There are also tests for extra dimensions. By measuring how gravity acts at the very smallest distances, scientists check for signs that space might have more directions than can be seen. Some ideas suggest that gravity might be stronger or weaker if it spreads into other dimensions. By building sensitive balances and tiny machines, people look for changes in the strength of gravity. But for now, gravity always acts by the same known rules. Scientists look for dark matter and dark energy by studying gravity too. They watch how galaxies spin and how light bends among the stars. If dark matter is real, its gravity should pull on the stars, even if no one can see it directly. By counting how fast galaxies turn and how clusters of galaxies move, people can estimate how much dark matter there might be. For dark energy, scientists watch how the universe grows and look for signs that gravity might work differently on the biggest scales. To test old and new ideas, scientists also try to find places in the universe where gravity is very strong or very weak. Near black holes, gravity is stronger than anywhere else. When light from behind a black hole passes near it, the light bends. By measuring this bending, scientists learn about the strength of gravity and see if it matches what Einstein's theory says. In places far away from all stars and galaxies, gravity is almost zero, but never truly gone. Scientists look for tiny movements of gas and dust to see how even the weakest gravity changes things. These small tests help show if gravity might stop working at long distances or if there is any sign of new effects out in empty space. On Earth, simple tools are still useful. People use plumb lines and levels to build straight walls and check the ground. These tools depend on gravity always pointing straight down. By checking these tools very carefully in different places, people look for signs that gravity might tilt or shift if there is something strange underground or nearby. Sometimes gravity is used in ways people do not even notice. Measuring the shape of the ocean, the depth of the ground, and the weight of heavy machines all use tools based on gravity. More careful use of these tools can even help find hidden rooms, buried objects, or oil under the ground. Medical science uses knowledge of gravity too. Doctors see how bones change in people who do not feel full gravity, like astronauts. They study how blood moves and how muscles weaken if gravity is less for a long time. This helps doctors make better treatments for people on Earth as well. Children, students, and teachers repeat experiments about gravity every year. Dropping objects, making pendulums swing, and watching how water flows down a slope all help people see gravity's effects in action. These simple tests can be done almost anywhere and help young scientists learn the basics of how gravity works. New experiments and machines are always being invented. Each year brings tools that are more sensitive and more exact. As science grows, people keep finding better ways to notice small changes or new effects. Many of these experiments give results that agree with current theories, but each test is a chance to find something unexpected. The search for new ideas is always guided by evidence. Scientists do not believe a new theory unless it can be tested. Every idea about extra dimensions, new particles, or new kinds of gravity is checked by experiments. Only ideas that match all the evidence are kept and become part of science. Science is careful work. Sometimes an experiment gives strange results, and many tests must be repeated. A single test is not enough. Only if many people in many places get the same answer do scientists trust what they see. By sharing information, checking results, and testing ideas, people learn more about gravity every day. Each question that is answered leads to new questions. If gravity is found to change in a new way, or if something like a graviton is found, scientists will build new machines to test what this means. By measuring, building, watching, and learning, science about gravity keeps growing. Learning about how to study gravity also shows the power of asking questions. Every time, from the simple drop of an apple to the waves made by crashing black holes, science grows one step at a time. Each experiment, each tool, and each person adds a bit to the story of gravity and the universe. Because gravity acts everywhere and on everything, the study of gravity will never truly be finished. There are always new places to test, better measurements to make, and more questions to ask. The tools may change, the ideas may grow, but the search to understand gravity keeps all of science moving forward. People continue learning about gravity by measuring, observing, building new machines, and asking more questions. As knowledge grows and the world changes, scientists begin to dream about a time when they can explain not only gravity, but also all of the forces in nature using just one simple idea. Many people work for years to find this big answer. They want to find a way to connect gravity with the other three main forces: electromagnetism, the strong force, and the weak force. If scientists can do this, they will have what is sometimes called a theory of everything. The search for a theory of everything is one of the biggest goals in science. People want to understand why the universe has these four forces and not more, and why gravity acts so differently from the others. Having a single theory would help explain why stars are born, how light travels, why the smallest pieces of matter stick together, and how the universe started. It could also give people new ways to use energy or discover things that nobody has seen before. To understand this search, it is important to remember what is known so far. Gravity is the force that pulls all mass together. Electromagnetism makes light, magnets, and electricity act as they do. The strong force holds atoms together, and the weak force lets some atoms change into others. Each force uses its own special rules, and for electromagnetism, the strong force and the weak force, scientists know what particles carry each force. For gravity, there is still no proof of a carrying particle. Scientists discovered over many years that when they use very strong machines and look at very small things, the weak force and electromagnetism begin to look almost the same. They have even built a theory that connects them into a single set of rules called the electroweak theory. This theory explains how some particles can switch between electromagnetic and weak actions, and it has helped explain how the sun shines and how some forms of light and energy are made. This was a big step, but gravity does not fit into this theory. The strong force which holds protons and neutrons together inside the nucleus of atoms is also very different from gravity. For the strong force and the weak force, scientists use quantum mechanics to write rules for how things work. These rules work well for everything that is very small, like atoms and the particles inside them. For gravity, the rules are not the same. Attempts to use quantum mechanics together with gravity often give strange results or numbers that do not make sense. This is a major obstacle. One way scientists try to connect gravity is by using string theory, where all forces and particles come from tiny vibrating strings, and where space can have extra directions or dimensions. In string theory, gravity is just a different movement of the string, and the math lets all four forces share the same basic structure. But so far, there is no evidence from experiments that can prove string theory is correct. The extra dimensions predicted by this theory have not yet been seen or measured. Scientists also look for clues in the largest parts of the universe. When they study how galaxies move or how the universe is growing, they sometimes see things that do not match what the present rules say. The presence of dark matter and dark energy may point to something more basic, something that connects all forces at a level people do not yet see. This idea makes scientists wonder if a theory of everything needs to include new things that have not been discovered. Another idea is called quantum gravity. In quantum gravity, scientists try to write the math for gravity in the same way as for the other three forces. They look for a graviton, a very tiny particle that would carry the force of gravity. But experiments have not found a graviton so far, and the math for quantum gravity is very hard. Many versions of quantum gravity exist, but none has become a proven theory. There are also ideas about hidden symmetries in the laws of nature. A symmetry means a rule or change that does not affect the outcome. In physics, certain symmetries help explain why particles are related and why forces can transform into each other. Scientists look for deep symmetries that could join all four forces. If such symmetries exist, they might show up as patterns in the way particles behave or in the rules that govern the universe. Physicists test new ideas with large machines called particle accelerators. When two small particles like protons are smashed together at high speed, sometimes new particles appear. These collisions can show how the forces work together and if anything strange or new is happening. With each new test, scientists search for small differences between what is seen and what is expected. Some experiments hope to find proof of extra dimensions, new particles, or new effects that would show how gravity fits with the other forces. The idea of unification inspires many people to search further. In the past, each time science put together forces, it led to new discoveries. Electricity and magnetism were once seen as different, but uniting them gave new tools like motors, radios, and lights. If gravity can be combined with the other forces, new science and technology could appear that nobody today can predict. Many experiments try to find new answers about gravity and unification. Some send detectors underground to look for particles that rarely interact. Others study gravity waves, light from the first stars, or energy from the oldest parts of the universe. Every measurement helps test if a simple set of rules might one day explain everything together. Some scientists look for evidence in the simplest parts of nature. If space is made of very small steps, or if time jumps instead of flows, new effects would be seen in the behavior of gravity or light. Other experts design experiments to measure gravity more and more exactly, searching for signs of extra dimensions, tiny changes, or new particles. The dream of a theory of everything shapes many questions. Will this idea show that gravity is made up of smaller pieces? Or is it really the smooth bending of space and time that Einstein described? Is there something deeper that controls all the forces? Or is gravity always going to stand alone? These are questions nobody can fully answer yet. Mathematics is the most important tool for this search. Every theory uses math to predict what should be seen. If a theory matches every experiment and fits with all other ideas, then people can start to believe it might be the answer. But when just one experiment gives a different result, or the math does not work, the theory must be changed or let go. Finding a theory of everything will mean testing every idea and checking every detail. It will take many more years and many people working together. Sometimes, new theories need new machines that have not been invented. Sometimes, new rules come from simple questions asked by new students, or from surprises found in the results of experiments. Even small steps forward matter. Each time science discovers a new link between gravity, light, and other forces, it brings more hope for unification. If just one part of gravity can be connected to the other forces, it may show all the way to a single theory. Scientists watch closely for every clue, every hint, every small difference that might point toward a better idea. The search for a theory of everything is full of challenges. It is very hard work, and often there is disappointment when new ideas do not match nature. But it is also full of excitement, because the answer will change how people see themselves, their world, and the whole universe. If this answer is found, people could understand how everything began, how it will end, and how all parts of nature are connected. This search is not only for experts. People everywhere wonder about how gravity and other forces work. Students ask questions about why things fall, why the sky is blue, how the sun shines, and what holds everything together. The search for a theory of everything begins with these questions. Many people work in teams across different countries, sharing their discoveries and helping each other learn. Some travel to remote places to build big detectors, others work at computers or look at stars in the night sky, and some think about math and try to find new connections. Every person adds a piece to the puzzle. As research continues, the path to a theory of everything becomes clearer. Sometimes answers come from unexpected places. A new observation in space, a new machine on Earth, or a new way to use old knowledge may show what makes gravity, light, and the other forces truly one thing. People may not yet know all the details, but every step, every question, every experiment brings science closer to putting the puzzle together. The universe, with all its stars, planets, and invisible forces, remains a place full of mystery, wonder, and hope. The future will be shaped by the answers people find about gravity and the other forces. As each new discovery is made, new uses, new tools, and new questions will grow. Each discovery will make it possible to see the world in new ways, to solve problems, and to build things that could not even be imagined before. Gravity, the force scientists and students started learning about by watching apples fall, may one day become the final link in a chain of knowledge. The search to fit it together with all other forces will continue as long as there are people who ask questions, look for answers, and wonder about how the world works. The journey to a theory of everything shows the power of human curiosity and the strength of people learning, thinking, and working together to make sense of the world and the universe. Understanding gravity is not just about knowing the answer to a hard problem. Gravity is a part of life on Earth and in space. Every single day, from the moment a person wakes up until they go to sleep, gravity is at work. It keeps people on the ground, keeps the oceans in place, and allows the air to stay close to Earth. so all living things can breathe. Without gravity, the simple things people do every day would not be possible. On Earth, gravity makes it possible for rivers to flow to the sea. It is the reason why rain comes down from the sky. When children play, jump, or run, gravity always brings them back to the ground. Buildings, mountains, and trees all stay where they are because the Earth's gravity pulls everything towards its center. The water in the oceans and lakes never floats away because gravity is holding it down. Every part of the physical world depends on gravity. When a person lifts a cup or throws a ball, they feel the weight of the object because of gravity. At night, the moon travels across the sky in a smooth path because gravity between the moon and the Earth keeps it in motion. Oceans move up and down in tides because gravity from the moon and the sun pulls on them. Farmers can plant seeds in soil and rainwater can soak into the ground, all because gravity keeps everything close to the Earth's surface. Gravity affects not just things on land, but everything in the sky as well. The sun rises in the morning and sets at night because the Earth moves in a path around it, held there by the gravity of the sun. Seasons change through the year as the Earth follows this path. Stars shine and planets move in their own orbits, always pulled by the force of gravity. Far away in outer space, gravity makes galaxies and clusters of stars stay close together. Without gravity, all of these would drift away in every direction. Life on Earth is deeply connected to gravity. The shape of every leaf, the way every animal moves, and the places where people build their homes all depend on gravity. Human bodies have bones, muscles, and blood that are shaped and made strong by working against gravity. When astronauts spend weeks or months in space, without the full pull of gravity, their bodies change. Muscles get weaker and bones lose strength. Plants grow differently and water moves in strange ways. To stay healthy, astronauts must exercise every day, and scientists must always plan for the effects of gravity or the lack of it. Oceans and air are kept in place by gravity too. Air pressure changes with height above the ground because gravity pulls air closer to Earth. This makes it possible for people to breathe, for birds to fly, for clouds to form, and for rain and snow to fall. On the surface, gravity lets rivers make valleys and helps form mountains over a long time. Mud slides down slopes and rocks collect at the bottom of hills because gravity always pulls things towards the center. Even time does not move the same way everywhere because of gravity. Close to very heavy things like planets or stars, time moves a little bit more slowly than far away in space. Satellites and clocks in space must be adjusted because gravity changes the way time passes. Without making these adjustments, tools like GPS would not be able to give good directions or information. Scientists use knowledge about gravity in medicine, building, travel, and many other fields. Doctors must plan for gravity when treating patients, especially those who cannot move. Engineers use the rules of gravity to build bridges, roads, and tall buildings that do not fall. Pilots and ship captains must know about gravity to fly or sail in the safest way. Farmers, builders, and people in almost every job use gravity, even if they do not think about it. Without gravity, the idea of home would change. There would be no safe place to rest, no soil for plants, no water to drink, and no air to breathe. Each meal, each breath, each step depends on gravity doing its work. The world has shape and order because gravity is always there and always working the same way. Gravity is also important for the future. Each launch of a rocket, each machine sent to another planet, and every plan to explore the universe must begin with careful study of gravity. Scientists who want to send people to Mars or to deeper space must plan for months or years when the pull of gravity will be different or missing. They study how gravity changes bodies, machines, and plants, and how to keep people healthy and safe in new places. Even as people use gravity every day, so much about it is still unknown. Scientists know how to measure its strength and predict its effects. They can use the rules discovered by Newton and improved by Einstein. They can build very sensitive tools to notice the smallest change in gravity, from the movement of water under the ground to the waves made when black holes collide far away in space. But when they try to join all the rules together, or to say what gravity really is in the deepest sense, questions still remain. Gravity's greatest mystery is that it cannot be turned off, blocked, or sent away. It always acts the same on all things with mass, from the smallest pebble to the biggest planet. Over centuries, scientists learned that gravity works across the very biggest distances in the universe and also affects the very smallest things, although not always in the same way as other forces. Details about why gravity is so much weaker than other forces, or why it acts only as a pull, remain open questions. Living with gravity brings challenges and also keeps people safe. Weather, oceans, and rivers may cause problems, but they are possible only because gravity shapes how water and air move. Each country and culture has found its own ways to use gravity for farming, building, travel, and play. Many inventions, from the simple plumb line to the most modern telescope, depend on knowing about gravity. Gravity is also a source of wonder. From childhood, people ask why things fall, or why the stars and moon move across the sky. These first questions can lead to a life of learning and discovery. The biggest telescopes, the farthest space probes, and the most delicate machines continue to be built, all to help answer questions that start with why and how. To keep learning, scientists test new ideas in the laboratory and in space. Each year, there are new discoveries about how gravity acts, especially as people look for things like gravitational waves, possible new particles, or hidden parts of the universe. These discoveries often bring more questions and help make science stronger by leading to new ideas and better tools. During the last few decades, teams of scientists around the world have worked together to build new detectors, better computers, and large telescopes. They share their results, check each other's work, and combine what they learn. Every new discovery is tested many times before it becomes an accepted part of knowledge. This careful work helps everyone trust the answers and build better ways to use gravity in daily life. Children and students everywhere can learn about gravity, not just in books or in class, but by watching the world, asking questions, and trying simple experiments. A ball thrown in the air, a cup dropped to the floor, or water flowing down a hill can show how gravity acts. Teachers help students make sense of what they see and ask questions about how and why gravity works. Science begins with noticing, asking, and testing, and gravity is a perfect starting place to learn these skills. Artists, writers, and musicians find inspiration in gravity too. The way planets move, the beauty of a falling leaf, or the patterns of the stars have inspired stories, songs, and pictures in every culture on Earth. The science of gravity and the wonder it brings connect both facts and imagination. The search for answers about gravity never ends. Even with all the knowledge people have today, gravity still holds secrets. Some of these might be solved with new experiments or by sending missions into space. Others might require new ideas different from any that people have had before. Science always moves forward by asking, testing, and trying new things, and gravity is always one of the biggest and most exciting mysteries. Not every idea will turn out to be right, but every idea that is tested teaches something valuable. Success and failure help grow understanding. Each generation builds on what came before so that new children, students, and scientists can reach farther than ever before. Science is a way of thinking that keeps improving, and gravity is at its core. The power of gravity is not only in what it does, but also in what it teaches. It shows that the world is connected, that all people share the same sky, and that mysteries remain to be explored. By learning about gravity, people also learn about working together, sharing questions, and building a better world. As new machines are invented and new discoveries are made, gravity will keep its place in science and in life. Every year, experiments become more sensitive, and new answers reveal more amazing things about the universe. The study of gravity is a journey with no end, always full of surprises. People's lives will always be shaped by gravity. It keeps the oceans, the forests, the cities, and the mountains in their places. It ties every person, animal, and plant to the earth. It reaches out to the sun, the moon, the planets, and all the stars. Gravity makes night and day, causes the seasons, and brings the tides and the rain. Life, in every form, depends on gravity to give shape and order to the world. Even as scientists hope to find a single idea that joins gravity with all other forces, what matters most is the search for understanding. The mystery of gravity reminds everyone that there is more to learn. Curiosity grows with every question, and knowledge grows with every answer. Gravity is always present. It ties together the land, the sea, the sky, and the universe. The questions people ask about gravity help them see that life is full of connections. Every action, every movement, every day is linked by this simple, invisible force. Exploring gravity leads not just to new science, but to a greater sense of wonder and a deeper respect for the world and the universe.